In my very first professional programming job, I had to write a financial report, the heart of which was an SQL query. So I worked and I got it working and I was very proud of myself until we ran it against the staging dataset. And it ran like an absolute slug. And then a more senior colleague of mine said, put an index on it. And I did. And it was fast. Brilliant. I now knew how to make databases run fast. You throw indexes at them. So I started throwing indexes at everything. And wouldn't you know it, the staging database starts slowly grinding to a halt. Perhaps you've already diagnosed why. But that was my first real-world experience of, if you actually want things to work properly, you have to understand a layer beneath. You have to understand something of how things work under the hood. So this week's kind of fun because we're meeting someone sort of coming in the other direction. I'm joined by Hannes Mühleisen. He's a professor and a database researcher, but as you're about to hear, he's absolutely not content to remain studying theory. He's come out of that ivory tower, and he's built one of my favourite new discoveries of late, DuckDB. Came recommended by a few colleagues of mine, and I've been really liking it. It's a local, convenient analytics database. It's fast. I like it enough that I should tell you this episode isn't sponsored by them. I just thought it was good. So I wanted to peel back the covers and understand something of how it works. And it turns out to be quite a treat, and Hannes is very good at explaining it. If you're curious about how a database can chew through a billion rows in a few seconds, or how you parallelize queries across multiple cores, when multiple cores seem like the only way that computers are going to get faster anymore, Hannes is your man. He's an excellent teacher. So let's go and hear from him. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Hannes Mühleisen. My guest today is Hannes Mühleisen. Hannes, how you doing?
Very good. How are you?
I'm very well. You're going to take me all the way down into bits and bytes today.
It's my favorite things to talk about, like these bits. I don't know what's so great about them, but somehow they have kept me occupied for a while.
They've been drawing us down since at least the 50s, right? So, but I want to get into your background first because I have to understand why it is you wanted to create what you created.
My background is, that's very interesting. Well, I guess not. It's a super vanilla of, sort of timeline. No, at some point in my life, I found computers. It was like 14 or something like that. And there's a fun story that I want to tell. So I had a computer that my dad sold me. Okay, he's a good businessman. It was discarded old computer, and it had a BIOS password, if you remember those set on it.
Oh, yeah, I do.
Yeah. And he didn't know anything about computers, and I didn't know anything about computers, but I just had spent all my money on this thing that had this, like, you turn it on and it showed you this password prompt, right?
Your dad sold you a brick.
He did. And I'm telling you, he's a good businessman. And then it's like, yeah. Okay, what's this password prompt? And there was no internet. People today cannot, conceptualize this anymore. But it's like there was no internet, so you can't just Google how to reset BIOS password. You couldn't just go to the library. They didn't know either, right?
Yeah.
So at some point, you found somebody who knew somebody who knew somebody who knew somebody who told you, like, take the damn battery out. And I think that's kind of, I don't know, it's this kind of way of thinking about problems. That they are just like a challenge, and they're just there to sort of, to be overcome, and not something that you have to give up on. Like, maybe it was lucky that the first problem was actually solvable, but
yeah. So your dad actually sold you a puzzle box and a career at once.
Kind of, yeah. And so then when I started programming like many kids with PHP and MySQL, I was one of the founding members of my hometown's MySQL user group.
Oh, cool.
I had a license plate with SQL on it because I lived in Stuttgart, and German license plates start with S. So
you're my kind of geek.
It's very bad. And then when it, I needed to study something, so I was like, all right. I was looking to forestry for a while.
Okay.
looking for a naval career, but then was like, fine, I'll study computer science. and yeah, so I did that, and then liked it. Went to Berlin, got my PhD in computer science. And
What's your
then
PhD?
my PhD is about distributed query processing, which is kind of the anti-thema of what we're going to talk about later, which is it's sometimes interesting to see, how careers kind of go. So then I came to Amsterdam after the PhD. Bit of an accident, kind of, because I didn't come here for like career reasons. I came here because I had a girlfriend here.
Oh.
And then I was like, okay, so I better find a job. So I looked around, and it turned out that there was one lab, the Dutch National Research Lab for Computer Science and Mathematics, that was hiring in a database group. And I thought, I wasn't in my SQL, user group. I could do this. And
I could query.
Of course, in a gigantic overinterpretation of my own knowledge, because anyways, it turned out this group was actually very good at data systems, at coming up with new ways to construct data systems. And so I joined as a postdoc, stayed like a tenure track, the whole thing. And ended up to be a place where very clever people have been thinking about data systems construction for quite a long time, for over like 20, 30 years.
Oh, wow.
And I learned a lot.
About the fundamentals of how we do querying.
Yes. Although in CS, you always have to be careful when someone says fundamentals, because very often they mean that they want to hurt you with Greek symbols. Okay. I am not about the Greek symbols. I want to make this absolutely clear. I'm a painfully practical person. It's so practical that I always wonder what I'm actually doing in academia. It's like, I was wondering a lot what I was actually doing in academia. It was just like, people literally told me, it's like, we're not here to solve problems. We're here to talk about problems. It's like,
that's rather cynical. But
I don't know. So anyway, so the you said fundamentals. That's absolutely right. We learn a lot about the fundamentals, but not in the way that some people might think fundamentals, as in like formulas and proofs and these kind of things. It was more like, no, here's a modern computer works, and here's how you have to sort of hold this computer funny so it actually solves data problems efficiently. So that was really all that was about. It's fundamentals. Yes, it was about query processing, memory pattern, access patterns, that sort of thing. We will probably go into that more later.
Yeah, I hope so.
Yeah, and then
yeah,
that was the academic. Then I even became a professor. I am still a professor. Officially on data engineering at the University of Nijmegen. I'm also still affiliated with the lab, the database architectures research group at the Research Institute, but these days I spend a lot of my time at DuckDB Labs, the company that we spun off at some point from the Institute around this DuckDB project that we started
Take
there.
me through that. How do you go from being a professor to being an OLAP database writer? Practical OLAP data, because that's the real gap between professor and...
professor that programs is almost unheard of, okay? Yeah. This is, again, you can call me cynical again if you want. And it's only been like 5 minutes of podcast, but professor that programs is pretty uncommon. So how does this happen? Well, I think in data systems, you can write papers, but it's kind of understood that a lot of your impact will derive from have you actually created any systems that are sort of relevant in the world out there, right? Have you created software?
That's unusual.
It's very unusual.
In academia, the writing of software is just,
Yeah, it's not respected a lot.
It's the turning of the handle that gets you to the paper.
It's true. It's not respected a lot. And it's also the quality of software produced in academia is also typically very bad as a result. Because it's just, as you said, it's a means to an end. You want to get your Nature paper is what you're going for. This sort of the R script that analyzes this, the result from your, telescope is like whatever.
Yeah.
But no, actually in CS, especially in practical computer science, especially in data systems, it is actually the case that the people that have gotten highest honors in our field, we have 2 Turing Award winners in data management systems, is Jim Gray and Michael Stonebreaker. they both have created actual systems. And
Would I know them?
Do you know them?
Well, would I know the systems?
Yeah, Postgres. So Stonebreaker was one of the people behind the creation of Postgres at Berkeley, way back when.
Right.
And they have gotten these awards not for their Greek symbol sort of fighting abilities, but more for they have actually built something. So it's, I think, in our field, and there's maybe some adjacent fields like operating systems that behave similarly. Like if you're an academic in operating systems, it does help if you have made some Linux kernel patches that turned out to be good ideas. Like I think it helps.
Right.
If you're in security, making tools is always going to get you some sort of credibility, right? So there's some adjacent fields, but it's not very common, I agree. So it was always very, it was definitely acceptable in this subfield to spend time writing software. We may have pushed this to new heights. I'm not entirely sure. But so when you come up with a new idea, you can write a paper about this new idea. Yes, you can build a prototype to show that your idea is a good idea. Sure. But people are only really going to take this seriously if this has proven itself somehow in the market.
Okay.
Right?
That's very unusual. To get ahead in academia, you need to push yourself out into the marketplace. It is.
I think there has also historically been a lot of sort of exchange between the academic teams and the teams in industry. Like you have in AI as well. Like there's a ton of people doing cutting edge AI research at Google. They're not technically academic people, but they are at the same sort of level. I think in data management systems, we also have had this for a while, that the teams at Microsoft that build SQL Server, the teams at Oracle that build Oracle, teams at IBM that build DB2, they had a very deep sort of knowledge in these systems, and the academics would frequently come from these teams, go to these teams, do sabbaticals there, go back and forth. So I think there has always been a pretty good exchange. But if you want industry people to take you seriously, you have to show that this can work in the marketplace, and it is a gigantic market. I think people underestimate this. So databases are sort of $1 trillion market or something like that, right?
I didn't know that, but I could believe it. Yeah.
So if there is such a huge amount of money flying around in this world, you can see how if you want to convince somebody that something's a good idea, you can show them hey, this is actually better. It's going to make you more money. It's anyways, there's always been a bit of connection. But so the reason I think we started programming so much in the institute was that we were sick and tired of the quality of research prototypes.
Right.
And we were like, okay, we actually want to have impact with what we're doing. And so when we started this DuckDB project, we were like, you know what, we'll do it, for real this time. Like we will have, CI on the third commit or something like that. We'll have testing in place. We will have coverage in place. We have all these software engineering tools that are pretty standard in industry, but unheard of in academic sort of systems. We will have all that.
Right. Yeah.
And we did. And so we also, it's also very common in academic systems to write the prototype until it can run the benchmark. It's pretty common.
Yeah.
You stop. Why would you add functionality beyond the benchmark when all you want is the paper?
To prove your idea, yeah.
Right.
Yeah. Okay.
But we said, no. This needs to be able to actually run general purpose SQL queries. But, in case I haven't said this yet, DuckDB is a SQL system, so it needs to understand the SQL language, the one that was on my license plate. The problem with SQL is that it is such a gigantically... honestly, I was totally blown away by this because I thought, SQL, I've seen some SQL. How hard could it be, TM? Famous last words. It's thank you, Jeremy Clarkson, for this meme of how hard can it be. And it's I was totally amazed. I only really learned SQL when we had to start implementing an engine that interprets SQL because people kept throwing queries at us and we were like, "Ooh, this is allowed?" And they were like, "Yeah, it's in the standard." We were like, "Oh, okay." Yeah,
I can believe that. It's you kind of think maybe it's got 20 or 40 keywords, but I bet it's a lot more and a lot more.
Recently I learned something about from another person that builds database systems. I learned something about that there is something called except all. In SQL, we have union, and people know that there's a difference between a union and all. Yes, you've heard of this difference.
Yeah.
It turns out there's also an except statement in in SQL with set semantics, but there's also an except all. And I didn't know about the existence of except all until this other person told me about it. But sure enough, it's in the standard, has been there since, way back when. So we then, we were like, fine, we'll have to implement that. So we spent a lot of time implementing this. We wouldn't have had this ambition of implementing the whole of SQL if we had just been out for a paper, right?
Yeah.
It only makes sense because we had been out to actually make a system that people use. And if you want to do that, well,
you kind of got to support SQL.
There's no shortcuts, really. Yeah. Like, just have to get through it.
But did you... Okay, so you're there in academia wanting to prove something. Did you start from, this is our topic of research, let's turn this into a product? Or did you say, this is what's missing in the world, so let's research that?
Yeah, I think the latter. We talked to people in, big data practitioners, and we found out that this was absolutely missing in the world. And what is this? We found that nobody had really considered sort of the ergonomics of using data management system. It was always very complicated to set up. Like it was, I don't know if you've ever tried to install Postgres or something, but you find yourself editing like some arcane config files and rebooting services and installing services and creating database files. It's not a very pleasant process, creating users, whatever. So one of the core sort of ideas that led to DuckDB was to say, look, there's a lot of sort of stuff that happens that actually makes it very hard to use these systems. Like you have to, as I said, you have to do all this installation, maintenance, blah, blah. Nobody has really thought about data management systems with like this user sort of angle. Like user in this case is like a programmer often or an analyst, but nobody had really thought about them in what's the maximum simplicity that you can get here perspective. Also, nobody had really thought about data management systems where getting data in and out of them is like a first principle, like that has to be fast.
Yeah.
Right?
Yeah, I've definitely dealt with plenty of systems where you get the database up and running, and then the big job is to figure out how to turn it into a schema and some insert statements.
Yeah.
Well,
and getting the CSV reader to work. Like I've tried the CSV readers of, 50 database systems in my life. They were all terrible, right? So we realized that a lot of the initial sort of interaction people do with data systems is A, the setup, and B, data import and export. So let's, maybe make that pleasant. That sounds like a good idea, right? Like this, because this is like the one time you have to make a good impression. It's like in these initial steps when the people don't know a lot about your system. They've just started. They just want to they would just want to play around or just want to get a job done. So we really designed this thing to be useful. So that was our academic angle. It's like, look, we need to reimagine these systems for usability. And
how do you mean that's an academic angle? Because seems more like a product industrial angle, UX.
Yeah, this is true. It can be seen like that, but if you think about it, we actually wrote a paper about this. The question is if you start from like these user interaction principles, like what I said, needs to be easy, needs to be good, have good efficiency for import and export. You can have a sort of an academic discussion on what does this mean for the construction of the rest of the system, right? So how does this impact like our canonical textbook architecture? And for example, there's one gigantic way in which it impacts the textbook architecture. The textbook architecture since like 1984 or so is this client-server sort of model, the two-tier system where you have database client, database server, funky line between them, right? That's a textbook thing.
Yeah.
But we realized that in order to meet these user interaction and data import efficiency goals, we needed to actually go to a different model, which is the in-process model, which is similar to what SQLite does. If you're aware what how SQLite works generally, it's this database as a library. You link it to your process. The thing runs in the same process. Okay, so now you're in the same process as your application. Well, that has a bunch of implications in terms of system design again, right? So, for example, you need to somehow cooperate with this application process. You can't just assume that this computer is yours, like typical data management systems do. Like, you have to sort of cooperate. You have to be very sort of careful in using resources. You have to be careful in how you crash. Traditionally, database systems handled fatal problems by just exiting, right? If you're an in-process system, you can't do that. because you bring down the host with you. So now you have to reimagine sort of fundamental properties of how we do, for example, transaction control and persistence under the premise that we cannot just exit when we don't like something.
It's not your environment to play with.
The environment. Another super interesting aspect there is like, if like databases are used to being coddled, like database systems, like Oracle is used to be run on very, very expensive hardware with like, some sort of a staff of nurses sitting next to it. Yeah. They're called DBAs, but it's the same thing, right? And like they have like memory correction in memory, they have redundant power supplies, they have giant RAID arrays to deal with hard disks failing and all that stuff.
Yeah.
If you make like that's so they can make certain assumptions about their hardware. DuckDB is made to run like on everyone's computer, their phone. It's made the simplicity and the way it's designed lends itself to run like everywhere on everyone's laptop, stuff like that. That's a very different environment. Like one of my favorite environments is the Brazilian Windows laptops. Nothing against the Brazilians, but they happen to occupy a warm place. And now you have a laptop that's maybe a bit older, that's sitting in like tropical heat, and then now you're trying to run serious sort of data crunching, that thing that's going to raise the temperature even further. The chances that your RAM starts like doing something funky goes up quite a lot, right?
Yeah, I can believe.
So there we had some issues where we're like, dude, your computer is broken. I can see from the bug report that your computer is just plain broken. But then, of course, the next question is again, like, how can we cleanly deal with this? So DuckDB now has a bunch of sort of self-checks that, for example, make sure that the hardware is doing something meaningful. That's one. So you can have you definitely can have an academic discussion, because like these UX kind of aspects, like you said, they are more traditionally more in the product space. But if you really think what that means for the rest of like this architecture that is so like well known, or so this follows these trodden paths where it's like you open like the thick book about databases. I can actually see it from my chair, the thick book. And it tells you how to implement a database system. Like page 743 will tell you this is how your transaction manager works.
Which book is that? What's it called?
This is called Database Systems. I think it's it's a Molina. Yeah, Molina is the author. It's a textbook. University students have to read it.
Poor university students.
Yeah.
Okay, so usability being both an important and academic concern, but let's talk about what DuckDB does technically and how it does it. I want to get down to this.
Yeah. Okay, so we're running SQL queries. Yes.
Yep.
If you strip away all the user interface stuff, our interface is like our what we get is a SQL query. And now we have to come up with something called a query execution plan, which is sort of a more sort of mechanistic description of the steps that we should do to compute the result. Because SQL is a declarative language. It doesn't actually tell you how to compute the result. It just tells you what you want.
Yeah.
It's the task of the SQL engine, in our case DuckDB, to come up with an execution plan to do that as efficiently as possible. So there's some aspects to this. So the first kind of steps you do is you try to bind the query to the schemas that exist and the types. And so then your types, these tables actually exist. That's a good thing.
Yeah.
And then you run optimizers. Like there's some static optimization that always are good ideas that you then run. Like you run like a symbolic optimizer that like these things usually are shaped like trees. Like you have operators stacked on operators, and they can have 2 inputs or 1 input or multiple. Like a join will have 2 inputs, an aggregation will have 1 input, these kind of things, right? Like these all plugged together to form your query. Optimizers will operate and then will say, aha, you're joining these 2 gigantic tables, and then you're filtering a lot of the resulting data out again on top here. Can I maybe move these filters into the inputs of these joins, so that I don't have to create this gigantic thing only to throw it away later?
Yeah. So pretty good idea. Rewriting.
These are rewrites that are like in this case of projection pushdown is what we call this, or selection pushdown. These are always good ideas. So you have static rewrite rules. You also have dynamic rewrite rules that depend, for example, on the cardinality, the amount of rows in tables. Now you have, for example, you have a join.
Yeah.
Say we want to do, want to join two tables together. Typical algorithm to do is this is a hash join where you build a hash table on one side of the join input and then you probe the other side of the join against that hash table.
Yeah.
Now, cardinality of your tables tells you, okay, which table is the bigger one. And it makes sense to build your hash table on the smaller one because the hash table has to sit in memory. If you build a hash table on a 10 billion row sort of table and then probe with 10 rows, that's very, very inefficient. The other way around is very efficient. So these are dynamic rules that then depend on properties of the actual data. Maybe they depend also on statistics like DuckDB or many other systems will know, for example, what the minimum maximum value in every column is, these kind of things, right?
Right.
So then you have your optimized plan. That's pretty standard. The Postgres does something very similar. Like I think any database system worth anything has like an optimizer that does these things. And then you get into the realm of the execution. Now you optimized your query plan. At this point, we tend to call it a logical plan. That then gets transformed into a so-called physical plan, which then says, okay, now instead of having a join, I'm going to pick a hash join. Instead of doing an aggregate, I will do a hash aggregate. These kind of things. You pick an implementation. You have a physical plan. You go to execution. Okay, so that's where it really starts getting like interesting. So now I should also say it's very important, for example, that these executions are parallel, right? Like that we use like DuckDB, like other database systems also in the space of doing data analysis on a large amount of rows. It's an analytical system. Needs to parallelize queries. We can't avoid it. Like it used to be optional, like 20 years ago, you could get maybe away with the database engine that was single-threaded because most computers did have one core.
Yeah.
Now my stupid MacBook has like 10 cores, right?
Yeah.
And you need to use all of them to get in. I mean, they're amazing cores, yes, compared to the one core from 20 years ago.
Faster, they've gone.
They are crazy.
Numerous. Yeah.
Yeah. I was blown away when this thing came out. Doesn't matter. We have to parallelize over these 10 cores. Okay, so then
out of curiosity, where does that decision happen? Is it as you finished optimizing and you're building the logical plan?
Yeah, no, actually in DuckDB it happens during execution. I will get to that.
Okay.
So now we need to actually execute this plan in parallel. Okay. Interesting question. Like, how do you automatically parallelize a Turing-complete language? Is not obviously trivial, right? It's okay. So these are all things that have to happen, and then execution will, compute things and come with a result. Now, how does this work? Well, the general approach is that you first separate your query into so-called pipelines.
Okay.
So you have your query plan, it's a tree. Now you look into pipelines. What are pipelines? Pipelines are things that can happen without so-called pipeline breakers. What are pipeline breakers? Those are operators where the entire intermediate result has to be assembled before things can continue. For example, say I'm aggregating, okay? I'm doing like a count star group by X or something like that, right? In SQL. Yeah. So now this operator can only start producing output once the entire input has been read.
Right.
Because, say I pick one group to output first, there might be relevant data for that group in the very last input row that I read.
Yeah. Or sorting, I assume. You can't output anything until you know which the smallest row is.
Absolutely. Yeah. Sorting is a great example as well. There's a couple of those join hash table build, the hash table build of the join. Also one of these things you have to read. So these are called pipeline breakers. So every time we encounter a pipeline breaker, we split the query plan up into these so-called pipelines. And pipelines means it's a bunch of operators that can run from a so-called source to a so-called sink,
right,
in a streaming way, right? So without
streaming in the heart of the idea.
There's streaming. There has to be, because you can't just naively, you could say, why would you just run one operator at a time? You take the input, you produce the output, and if the next operator runs and so on and so forth. That's like what pandas does, for example. If you know pandas, like this Python tool to wrangle data run. And that's a terrible idea, because the materialization between operators that could actually stream data through is a terrible idea, because it will have to materialize this stuff in memory somewhere. which creates memory traffic between your CPU and memory. And that will take a lot of time, and you might run out of memory, and it's generally not pleasant.
Whereas you could have stayed all in the CPU, is that what you're saying?
Well, whereas you could have just streamed a chunk of data to multiple operators at the same time, and that indeed would be staying in the CPU cache much more likely. If you look at something like Postgres, they go to the other extreme. They do like a row by row thing. So Postgres reads like a row of input, applies the next operator, applies the next operator, applies the next operator, and then produces output or not. SQLite does the same thing. Right. And that's really great for systems that deal with small sort of result sets or small input, like the transactional systems tend to do, like update an order. You don't really look at 10 billion rows, right?
Yeah.
But for analysis, this like switching between operators, switching across the types that could potentially exist in a query actually creates a lot of overhead. So therefore, we have to find some middle ground. So what DuckDB actually does is implements a so-called vectorized query execution engine. So what does this mean? We have our pipelines that are streaming.
Right.
Probably multiple operators in a pipeline like this, like a filter, like a window. Some window functions could run in a streaming way. And projections can run in a streaming way. These kind of things, right?
Yeah.
And now we don't do the full materialization, which would be like running one operator at a time and writing stuff from memory every single time. We don't do the Postgres thing and reading one single row every single time. We do something in the middle. We take, in DuckDB's case, we take like 2048 rows.
Right.
Just as experimentally found to be a good idea to have 2048 rows.
Right.
Like it used to be 1024. It eventually, as I will explain why this number exists. And then you basically take like these vectors, we call them vectors, like subsets of these intermediate results, and then we stream them through the operators. And it's important to know that this is a column-first representation. So we don't have single rows that we shove through the operators. We have like little chunks of columns that we shove through the operators. That has big advantages because we can then have a columnar sort of processing, which allows us to be more efficient in terms of branch prediction, which is the CPU basically trying to figure out where your code is jumping next. And it uses a statistical model for that. And if you do the same thing all over again, the model gets better. Right. And so this is the reason why columnar representations are better in this, because the branch predictor will be better at predicting where you're going next as your amount of sort of stupid repetition increases.
Right. Yeah, that makes sense.
And if you did this row-wise and you had to do something else for every sort of field, because the fields are different types and different things happens to them, then the branch predictor goes like, I don't know.
You seem to be doing 10 different things at once.
Yeah, exactly. Yeah. A lot of things happens here. I have no idea where you're going. Yeah. So this is why doing this in a columnar way is better, because the branch predictor will tell you you're going there, and it will be right. And if it's right, it will also do speculative execution. So the branch predictor will actually say, based on my amazing statistics, I'm fairly sure that you're going to go this branch. So I'm actually going to already schedule this branch for execution in my CPU. And only if I realize that I was wrong in my prediction, I will abandon all that effort and actually do the other thing.
Right.
So that's actually quite a powerful thing. So this is why we have vectorized execution. We want to be one reason why we have vectorized execution. We want to be good on this branch prediction. But the other thing, and that you mentioned this already, is that by controlling the amount of like the size of the intermediates, like the size of whatever intermediate results goes between these different operators that are in a pipeline, we can make the query execution stay in the CPU cache for longer, and ideally forever. And that's where the 2048 comes from, right? Because the CPU caches in modern CPUs are actually quite big. Like they don't sound big. There's like, oh, it's 32 megabytes. But 32 megabytes is quite a lot of storage.
Yeah, that used to be a whole computer.
That used to, yes. I mean, my first computer had 8 megabytes of RAM.
I think my first had 512 kilobytes.
There you go.
We sound.
Like that's, and now that's cache, right? That's like on-die CPU cache. And you have 32 megabytes of them. Okay. But point being, by controlling the size of the intermediate with like this stupid constant like 2048, we can keep this stuff in the CPU cache. And why is that important? It's because of the memory hierarchy. Like as the the storage has this whole hierarchy. We have the cache sitting on top. Actually, on very top sits a CPU register. That's the fastest thing. It's one cycle to access. Very nice.
Yeah.
And then you have the caches, and then you have main memory, and you have storage, and you have tape, and you have internet or whatever, right? Tape's still a thing.
Really?
Yeah, people, it's the cheapest medium to do backups on. It's really like tape costs nothing, right?
Okay.
It's just tape.
I haven't seen it in a while, but I can believe.
Sure. No, I think if you can actually, the cloud still has it. If you use Amazon, what's it called? Glacier. Yes, It will be on tapes. Yes.
Oh, I didn't know that was tape.
Yeah, this is why it takes them 4 hours to get your data back, because it's like, hang on. Anyways, we want to be up in the storage hierarchy, ideally in a register, but we do data processing. We can't be in a register, but we can be in cache.
Right.
And by staying in cache, we can get like 100x kind of speed improvement compared to if we had to go back and forth to memory all the time. It's actually something that was invented here in Amsterdam at the CWI. At the institute that I used to work. Yeah, I told you they knew something about things. They invented this whole vectorized query execution paradigm, specifically colleagues of mine, Peter Bons, Marcin Sukowski, and Niels Ness. And it's very interesting because Marcin is now one of the guys that founded Snowflake. It's like there's some interesting connections in that world. And Peter is also a professor of data systems here, and he's also. Anyways, there's this. It's a very small world. These data systems.
And the Amsterdam Tech Hub investing in people.
Yes, well, investing. Yeah, it's the government, right? Like it's a government agency that does this. Anyways, the vectorization, that's really a key ingredient. And I should note that there's a competing approach.
Oh, okay. Tell me about that.
It's a competing approach. So you can do vectorization, which is what I just explained, or you can actually do something called JIT, just-in-kind compilation. So there's also a bunch of SQL engines out there that basically ship a gigantic C compiler with them.
Right.
I'm not kidding. They just embed LLVM. Done.
Right.
And then you could also try to convert your SQL query to a C program, or like assembly program, throw it into a compiler, and then run the result. That's a competing approach. Then you also don't get a lot of interpretation overhead like you do from like looking at the types and operations every time for every row that you would otherwise get. But with the JITting, you can also basically fix that by just saying, okay, we'll just create a binary for this particular query. We'll compile a binary for one specific query.
Is that then a favorable approach when you tend to run the same query over and over?
Yeah. Yes, that definitely helps. It does help for transactional use cases where you have a lot of prepared statements. It also helps, if you have very, very long expression chains, things like that. The big downside, however, for JITted engines is that they have to ship the gigantic compiler with them. And actually, that was one of the things that followed from our first principles, that we can't do that. Because you said, hey, look, this thing needs to be easy to use and easy to install. Part of that is the binary can't be like 2 gigabytes. But
and can't depend on you having a certain tool chain available.
It can't depend on you having LLVM with exactly the right version, by the way, installed, because
a few of us have been there. Ouch.
So therefore, we couldn't use JITting. That is one of the things that followed from our sort of high level sort of assessment of, what should this thing do? How should it behave? It's like, I can't use JIT because it's not going to be economical. It's not going to be portable. It's not, it's not going to be nice. And also, there is a research paper written by the proponents of JITting and vectorization that have essentially come together, wrote a paper proving that the approaches are essentially equivalent. So, hey.
Allowing for time, presumably.
I'm sorry?
Allowing for time.
No. The time also equivalent as in like.
Oh, okay.
Equivalent as in like execution performance.
Oh, okay.
Yeah.
Okay.
No, the vectorization gets to the same sort of speeds if done properly. So we have this vectorized thing, which is really cool. Right. So it does make it a bit more complicated to write these operators, because now instead of like writing like a projection where you do an addition of 2 columns like A plus B, you go like if you had like a simple old school system with like rows, it would be pretty obvious how to write that. You have like a loop, and then it goes like left plus right, left plus right, left plus right, and so on and so forth, right? If you want to do this in a vectorized way, it's like, oh, now all my sort of math operators actually operate on these arrays of data. They're like, there has to be like code being generated with templating that expands all these, things into like loops, and you have to do like null handling, and you have to do like all these things. So you get a bit more complexity in the operators themselves.
Because you're constantly dealing with a batch of 2048.
Yeah, you're constantly dealing with these batches, right? Also, like if you do like an aggregation, you're aggregating 2048 values at the same time, like that. Sometimes it takes a bit of sort of mental gymnastics to do this well, or like to wrap your head around how the operator actually has to be implemented in order to be efficient when dealing with a lot of values at the same time. Or like an index lookup, right? Traditionally, you did like an index lookup where you have like one value, you walk down your B tree, there's your thing. If you have 2048 search values, you're like, how do I do traverse now, right? Like it has some...
And there must be, you could just do it 2048 times, but there must be more efficient ways to walk down a tree.
There is, yes. You could have 2048 pointers in the same tree, because then you kind of try to reuse the same I/O. But of course, also problematic. You can't have 2048 outstanding I/O requests. Blah blah blah.
Yeah.
Complications. But hey, people have PhDs for a reason, right? Like it's we have done nothing else in the last 10 years than to think about that. So that's fun. But so that's the vectorization stuff. Yeah, it does slightly complicate your operators, but from a user's perspective, it's great because stuff stays in cache, so it's really, really fast. You as a user, you don't really see that it's a vectorized system anyway. You write your SQL query and poof, out comes a result, right? Like, it's a very sort of detail on how the implementation works. But it is the thing that DuckDB does, and it's kind of cool because I think in DuckDB, like one of the unique things is that we combine like this crazy academic sort of knowledge on how data systems should be built, all wrapped into a package that's like try to be friendly. And that's, I think, something that I don't think has been done before. Like, as in, like, the state-of-the-art stuff tends to be like a bit clunky to use. And the stuff that's easy to use, I don't want to name names, but there are some data management systems out there that try to be very easy to use, but then have like serious issues in sort of the internals and how they deal with things like persistence, right? Because they compromise all of that away.
Yeah.
So we kind of have both, right? We have this like crazy core that uses like really the state of the art in query processing together with this friendly interface. But I want to talk about something else. I want to talk about parallelization.
Okay.
Because that's also really, really, really interesting. So parallelization, many cores. Yoo-hoo. Yeah, we have. So there is an interesting paper from one of the greats of data management systems research, Götz Gräfe. I don't know if you have heard of him. His name, he's German, like many database people. I don't exactly know what it is about tables, but somehow it appeals. Somehow it appeals to the Germans. But
no comment.
It's
minds. Yeah.
It's really uncanny how many Germans are. And it's like you go to the US, it's like, oh, also a German person. Aha. Not only, of course. Don't get me wrong. There's many, many, many different sort of people working together. It's just it's an uncanny amount of Germans, and there are more than there should be. Okay. Anyways, so Götz Gräfe, one of the greats, he wrote a paper in like the 90s or something like that about it's called Volcanoes, the volcano query processing or something. Volcanoes in the title. You will find it if you go for that.
I'll put a link in the show notes when I find it.
And in this paper, he also described how to do parallelization.
Right.
And so that's actually, as I said, it's a difficult problem. You have your query plan, and now you want to run this on many CPUs. What do you do? Well, Dr. Gräfe, he came up with this idea of the exchange operator-based parallelism, and it at the time it was very clever because it's a way of doing parallelism that doesn't impact the other operator's implementation at all, which is great, right? If you want to get something done, it's great if you don't have to throw your rest of your system away. Like it's always good if you want to get something through. Like, here's this cool idea, and by the way, it works with what we have. So how does this work?
Okay, yeah.
Exchange, by the way, DuckDB is not using that. It's just what everybody else is using. And I'm going to say why it's bad in a second. But so exchange-based parallelism works like this. Say we have a filter.
Yeah.
And we want to parallelize the filter. Okay?
Yeah.
So now we insert this special operator under the filter that splits up the incoming data stream into, let's say, 8 data streams.
Yeah.
Okay? Into 8 data streams. You can kind of, hang on, I have too many fingers. This is 8, yes.
Yeah.
And now you run this filter on every one of these 8 data streams in parallel. Haha.
Yeah.
And then you put another operator on top that collects all the output of those filters back into a single data stream.
Mm-hmm.
And now you have successfully parallelized this filter. Okay?
This sounds like MapReduce.
Aha. Yes. It does. I mean, MapReduce came much later, of course. So who got this from whom is it's pretty clear in this case.
Okay.
Point being, okay, this works really great for filter. Yes?
Yeah.
What about an aggregation now? How does this work? Because obviously, I can't just use my little distribution operator to have 8 input streams, run my aggregation on all of these 8, and then just glue together the result again, right?
You can if it's sum. It's a little trickier if it's average, that kind of thing.
Yes.
Yeah.
You can do that, but then you have to actually reinterpret the results. You have to then remap the groups together after all these operators.
Right.
And there can be millions. So then you've spent a lot of time on the remapping. So that's really not the point.
Right. Okay.
So what this exchange-based operator parallelism does is it introduces a hash partitioning on the group key in the distribution operator, saying, aha, if I hash the group key in the distribution phase already, and I do a radix partitioning based on bits in the hash between all these 8 data streams that I'm creating in my distribution operator, then do the aggregation, and then I can be sure that I can just glue all these results together again, and the result will be semantically correct. Because, we can prove that only data that matches, like from this hash partition, went into this one group by operator. And
so you're saying if I'm doing select some average of something group by user, you're going to hash the user ID and chuck
Yes.
Same, chuck the same
and split it
user
up
ID
like that. Yeah,
buckets.
exactly.
Okay, yeah, that makes sense.
So that's how it works, right? This is also how the joins work. They will say, aha, we'll split both the build and the probe side of the join using the same hash partitioning, and then we can run this in parallel, and then we can do the recombination, and everyone's happy. Well, there's some issues with this. And can you spot any issues already?
I would have thought, like, if you're trying to split it up into 8 chunks, going to disk, then you've got a big problem. You're basically you're reading the disk. It's going to be hard to parallelize pulling out the different bits of disks and then repartitioning them into different groups, right?
Yes, but it doesn't have to go to disk. This is like a stream thing, right? Like, so as the data on the fly, it can do this partitioning.
Oh, okay. So it's streaming in batches.
It doesn't have to. Yeah, it's streaming. Okay. So there's two main issues with this. One is the fairness of the partitioning. Okay, so data isn't nice enough to be sort of uniformly distributed across all dimensions.
Yeah.
Right. So what happens now is, like, what happens if my group key is like highly skewed? Like, I have 10 billion rows with the same group key, and then I have 10 billion rows, but they all have different group keys.
Yeah. Plenty of businesses have a few users that
heavy hitters problem. I like to call it the Justin Bieber problem. Like everything is, like if you look at like social networks, they're all like following on these like massive nodes that have a lot of connections. Same problem. So if you now do a hash partitioning on those, what happens is that one of your cores will be very busy with the heavy hitter, because one of them is unlucky to get the hash partition where the heavy hitter sits in.
Yeah.
And all the other ones are sitting there
around idle. Yeah.
Right? Or doing something, but obviously the runtime of the biggest partition will determine the end-to-end runtime of this query.
Yeah.
Like, so skew is really terrible here because skew kills the fairness in distribution. The other thing that's really terrible is it's not reactive. Once I start partitioning this into 8 partitions, I am doomed to keep partitioning this till the query is completed, because I cannot just change my mind and do fewer partitions because my downstream operators don't know about this, that this is going on in the first place, because I've tried to avoid rewriting them. And therefore, I cannot really change my mind. Usually the exchange-based parallelism is baked into the query plan. So they actually have a step that takes the physical plan, inserts these operators that split up and recombine, split up, recombine. And it's really problematic for skew and just reactivity reasons.
So is that like if I've got 10 million rows and the first million are skewed quite differently to the last million?
That, but also something like, say a second query is coming. I can't just hog all the cores while I'm processing the first one. Second one will have no resources to use. Maybe I actually want to go down with the number of cores that I'm using for the first query, because now I want to distribute my resources.
Oh, I see. Yeah.
It's actually one of the issues that's really plaguing Spark. I don't know if you have experience with Spark. Regrettably, I have tons of experience with Spark. Apache Spark. And they use exchange, but they just implemented Gutz's paper, right? They use exchange parallelism. But as a result, Spark classes are sometimes used by multiple people. But if like somebody gets lucky and grabs all the cores for his query or her query, the second guy or girl coming with another query has to wait till the thing's finished, because they have baked in this parallelism in the query plan.
And they're waiting for the whole thing to end, and it might be that 7 of the cores are idle anyway.
Yeah, you don't know, right? So there's some ways of fixing this with like overcommitting and blah, 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 but you could also abort the query and redo your partitioning. We'll ignore all of this now. So this is why the state of the art isn't this system anymore. Instead, we use something else. We use morsel-driven parallelism. Now, how does this work? Morsel, yes. So there's another paper at VLDB, the very large database conference, that explains how that works, where we basically say, hey, this idea from Gutz from the 90s, try to avoid redoing the operators for good reasons.
Yeah.
Maybe that we can now start hacking these operators, and we can avoid all these problems that come from this operator unaware parallelism scheme. Like the operator doesn't know about parallelism in the exchange-based system. In morsel-driven, the operators do know. So I already told you how the operators become more complicated because they have to be vectorized.
Yeah.
We're adding a whole level of complexity now to make them parallelism aware now, which makes it even harder to write these operators, okay? But for good reasons, because of what morsel-driven parallelism does, it says, look, we will not bake these extra operators into the plan to make parallelism. We will actually make the plan itself parallelism aware. And this comes back to the pipelines I mentioned earlier. The pipelines are streaming from a source to a sink. Sources can now basically split up their source into multiple chunks, but not with any lot of logic. They can use whatever partitioning scheme they want. They can just say, you know what, the first 10 million rows go here, the second 10 million rows go there. It doesn't matter anymore. You just, like, if you do a table scan from disk, you will look at your metadata and say, aha, I have 10,000 blocks, so I guess the first 1,000 go to core 1, the second 1,000 blocks go to core 2.
Right.
And now we've lost this partitioning scheme that the previous method relied on, right?
Yeah.
Okay. So that means that we have some semantics issues in our operators. However, only blocking operators have these semantics issues because they have this whole data set view, like a group by, like a sorting and so on.
Yeah.
So now those are the ones that have to be adapted to basically be able to work with multiple streams of data from multiple pipelines that run in parallel, coming into an aggregate, for example, at the same time. And then this operator, this aggregate operator, this parallelism aware operator needs to know how to reconcile this. And in the case of the hash, that you can imagine that, you're building more hash tables. You're trying to figure out which data is in which sort of group. You're trying to add a secondary sort of recombine phase, like you just said earlier. It's all sorts of tricks you can pull. It does make the thing more complicated, but there's a great upside because there's no longer a fairness issue. If we can have n threads working on this, and they're just grabbing subsequent tasks from these sources. And if we want to have n minus one threads working on this, we'll just wait till one of them is done, and we'll have the thread do something else, and nothing bad happens. It's no longer this stream that has to has to be orchestrated to run in parallel for it to work. It's more like a list of tasks that you sort of go through, and how many threads go. The more threads go through these tasks, the better. But it's no longer no, it has to be 8 and they have to be running at the same time.
Right.
Similarly,
is it that the source can dynamically react as it's splitting up that disk?
No, it will just generate a bunch of tasks, and the worker threads will grab those tasks.
Oh, I see. Okay. Yeah. Right.
Secondary, we had this fairness issue with the Bieber problem, with the high hitter group. That's no longer an issue, because it means, yes, one of your threads will be first of all, we don't have these all in the same thread, all these groups in the same thread. This is the problem of the upstream operator. And if one thread takes a little bit longer than another, not everybody else is blocked, because they can go and fetch the next task already, and be if this guy takes a bit longer, whatever. Right? So you can just grab another task while this guy is still doing this thing.
Okay, yeah.
So this it's very elegant. It's very elegant to use this morsel-based parallelism. It's a very sort of effective way of doing parallelism, and the result is that DuckDB can basically parallelize arbitrary queries over all the cores that you have. You can also tell it to use fewer cores. It can dynamically react to say, oh, now we have 2 queries running. We probably shouldn't give all the resources to the first query, but maybe we should give some resources to the second query as well. All these things become possible. And the only cost, quote, quote, is of course to the poor people that have to implement this. So some of the people in the company here that, or myself, I've done this too.
Yeah.
Now have to implement operators that are aware of parallelism, aware of this morsel-driven scheme.
Well, that's the whole point of getting a database engine, so you can force other people to do the really hard computer science for you, right?
This is indeed. It's it's the same with lots of CS, right? If you look at how the CPU works, or how the operating system works, or how your phone works, the baseband in your phone works, a lot of really, really hard complexity is hidden from people behind somewhat efficient user interfaces. In databases, this is the same, right? We do all this crazy stuff. And these are just 2 examples. There's more crazy stuff happening, of course. So in the end, the user just goes and types a query, and the thing, will process this in as fast as short a time as possible, using these crazy tricks to get your CPU to be as efficient as possible on this. It's quite interesting. You're kind of you're trying to wrap the ugly parts kind of to hide them from users. But there's these two things. They're the vectorized query processing and the morsel parallelism. They're really fundamental, let's say, to the whole thing. I would say those are those characterize how the system works.
It's interesting how the strategies involved are familiar, even if the domain isn't. So the idea of splitting things up into medium-sized batches and stream processing them where possible, and the idea of rather than having a really dynamic scheduler or something, you just have chunks of tasks to be dealt with as they come in.
Yeah.
Those are familiar outside of the database world.
Yeah. Absolutely. There's absolutely. I think one of the complexities in database world compared to say other systems that support exposing this, you mentioned MapReduce in the olden days, there was Hadoop,
yes.
to everybody's great great entertainment.
It was pioneering, let's say that for it.
I think the difference of data like SQL databases is that there is this crazy complex language that people throw at us. It's pretty obvious to do this in a straightforward query, select blah from the group by bar. You can draw this I can draw this on a whiteboard, explain this to students or DuckDB users. Once this becomes 15 joins deep, various aggregation levels, window
Nested
functions.
subqueries. Yeah.
Nested subqueries, a good one. Yeah. We actually have implemented another paper from a group from Munich, by the way. We have colleagues from Munich, also academics that also, by the way, also work on actual systems. The team that is behind Hyper and Umbra, Professor Neumann and his team, they've written a bunch of great papers on how to solve some of these really ugly issues, specifically one around nested subqueries.
Okay.
That's something that one of my the co-creator of DuckDB, Mark Asfeld, who's sitting next to me here, he at some point disappeared for a couple of months with this paper and reappeared only when subqueries were kind of solved. And it's to this day, it's still I still have my highest respect for Mark for pulling this one off, because like subquery unnesting is one of these things that, like 3 people in the world know anything about. You know what I mean? Like there's this guy, there's Professor Neumann in Munich, there's Mark, and maybe one other person that understands this. And it is fun, right? Like because usually people don't do this. Like, and Postgres, by the way, cannot do it. They cannot unnest subqueries.
Why not?
Because nobody has ever Postgres has ever bothered to implement Professor Neumann's seminal papers unnesting arbitrary subqueries. Okay. Right? Like it's there. It's just very difficult. But once you've done it, you have no more. Like the nested subqueries actually disappear in your execution, which is great. Like that's like a factor 10 million query speed up right there, because you don't, instead of sort of having to do this dumb re-execution of your nested queries for every row.
Yeah.
You actually turn it into a join or an aggregate, and that's it. Like, I can recommend, if somebody has a lot of time on their hands, I can recommend reading this unnesting paper.
Oh yeah, I bet that's quite easy in the simple case, but getting it to be semantically sound in the complex cases.
Yes, and they actually can prove they can do it in all cases, and it's exactly what you want, because then you can throw away your other implementation.
Right.
It's like you want to be able to optimize all of them away. So there's a lot of these things. There's also like fun stuff around like window functions that like nobody like. You heard of window functions in SQL, right? Like this idea that you can look around a bit, or you can also say, like let's add up the previous 2 and the following 2 rows and things like that. Like normally in SQL, that would be like 4 self joins or something like that. It wouldn't be pretty.
So you can take the difference between this one and that one. And finally, what we all want to do, differentiation in the database.
Yes, exactly. Well, what people do with this thing is really beyond me. I mean, I'm remaking database systems. What people do with it is entirely different. We talk to people. We want to know. We want to know what they do with it, because, we want to see something. But like sometimes what ends up on our issue tracker is like, what? Okay. But to come back to window functions, there's also one of these things, right? Like there is maybe, I don't know, 10 people out there that know how to efficiently implement window functions. And because, usually your database does it for you, but if you're the person that has to write this thing, it's not going to be pretty, because you're suddenly very, very alone. And you're very grateful if somebody, and in this example, also the Munich group has written a paper eventually. You're very grateful if some crazy academic out there actually wrote down what it takes to do this efficiently. Like that. That's something that we're really also really grateful for, standing on the shoulders of giants, like people here in Amsterdam that we learned everything about vectorized query execution from. People from Munich that we learned everything about unnesting subqueries from. Like it is a big advantage of being in the research community, of just knowing where to look, I guess.
Yeah. And having a bunch of people that have not only done the work for you, but proved it's going to work.
Well, they haven't done the work for you. Okay, they don't publish code that you can, like, code transferring code between database systems is really not happening a lot, right? Like nobody has. I mean, nobody's going to copy paste the optimizer from Postgres into MySQL or something like that. It's just not going to work, right? You have to re-implement it.
They've done the thinking work for you.
They have definitely done the work, and they have bothered to write it down. Like I think a lot of, and it's not going to be a patent like when Oracle does something like that. It's complicated enough. It usually ends up in a patent, and you can't touch it, right? Like it's when somebody writes a research paper, it's a very it actually helps other people. But as I said, like building these kind of systems, you end up being alone a lot. Like you end up being the first person to come in across this problem ever, or like in recorded history or something. Like there's nobody else you can ask, right? It's not like with this computer that had a password on it. There's nobody you can ask.
Yeah, but that's the joy of academia, right? The worst situation is I can't find a single problem that hasn't already been solved.
Yeah, I have a bit of a rant about that. So especially the Greek department, like the people with the symbols.
Yeah, right. Yeah.
They are masters at like inventing problems, and then solving them. And then there's a paper, and then like everybody goes like clap, 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 clap. But in our field, like it always bothers me when people kind of design, into thin air, or design based on sort of imaginary problems, because there's so many actual problems in data out there. Like so many people are struggling so hard to process data. To like, if you look at what people are using out there, like people are on pandas, like they're running pandas, which is this. I mentioned it earlier. It is this full materialization query engine from like, state of the art of maybe mid 90s or something like that, right? Like it's not great, but it's the only thing people have. And then when the academics who actually know something, know better how to build these things, then decide to throw symbols around or decide to design something for an imaginary use case, then it bothers me, because it's like, look, we have all these people out there on pandas. Can you just do something for them? It's actually our Turing Award winner, Professor Stonebreaker. He's at MIT. He has coined the term of solving the whales problems.
The whales problems.
The whales problems. Whales being like Google and Facebook, and
yeah, right.
And I think as an academic, it's actually quite criminal to try to solve the whales problems, because the whales don't care. They have clever people. We worked with some of the people at like Facebook, Google, and so on. They are clever people.
Yeah.
They don't need us to solve their problems. They will ignore solutions that we have come up with anyway.
Yeah,
and now we are spending like tax money on solving Google's problems. Like, what is this saying? Like, what is the sort of the moral story here? I have another example. Like when we started DuckDB, we said, okay, distributed query processing. The topic I got my PhD in is not going to be something that we're going to do, because it's absolutely idiotic to start throwing distributed systems at like 99% of data problems. But that's not an acceptable view in academia, because they say, yeah, but Google has all these big data sets. Like, how can your solution be relevant and meaningful and sort of valuable if it doesn't solve the 1%ers problem? But our point was to say, look, if the 99% are still sort of on pandas, clearly, something needs to be done. So we were always saying like, no, we're not going to touch distributed systems. And in my opinion, it was the right call, because the computers get so fast. You can easily go terabyte data processing on your MacBook these days. It's and there's also this interesting effect that I've noticed, is that hardware scales faster than data sets, because the humans scale slower than hardware. So we have like a natural limit on monkeys hitting like keyboards, right?
Right.
An amount of meaningful, valuable data we can produce is just limited by the amount of people that we have. We have 8 billion, seems like a lot, yes? Or 9? I don't know, actually don't know the number. Do you know?
Yeah, it's 8 to 9 billion.
8 to 9 billion. Yeah. It's not going to be 20 billion next year, but the MacBook is going to be twice as fast next year.
Yeah, yeah.
So actually many data problems are actually just eaten up by hardware, right? So spending a lot, and you have no idea how much sort of brain time and sort of thinking time went into distributed query processing. It was like, clearly the data problem is going to be so big that we have to have multiple computers. And this was true. If you're Google, sure, I believe you. You have your search index; it's gigantic.
Yeah.
You need this, but then you have people that are getting paid very well to deal with this, and I don't have to spend my time on this. At the same time, if I can show that any meaningful data set that people see in the world fits on a MacBook, that's where I want to be. That's just my ethos as a researcher paid with public money. I mean, it's like it's
nice to see. I often think like industrial programmers often complain that there's nothing new in programming since the 70s. And I think, well, it's because we're not looking. There's that bridge from industry to academia isn't there. There are new ideas, and we're not implementing them.
Yeah, it's true. Yeah, it's a fun problem. But it's one of these things that I'm sometimes wondering why funding agencies, for example, don't mandate something like this. Like there are enough problems out there. Just look at them.
Yeah.
It's like just look at the world.
No shortage of problems in the world.
No, we just picked one, and then hey, it's really annoying to process data.
Like, in that case, perhaps I'll feel better about pulling out to my specific use case of DuckDB, and we can talk about that quickly to end. So, I started using it. I found DuckDB on the recommendation of a friend of mine because I have a bunch of modestly large JSON files that I wanted to do queries on. And had faith that I could use Postgres or SQLite, and it's not that hard to create a schema that matches the JSON and all the . But then I just chucked it into... I didn't even chuck it into DuckDB. I did select star from JSON file name, and it just works.
Yep.
And firstly, that raises applause, making it that usable. But then I'd like to know what's going on under the hood for that. Is it actually... Is it parsing is it creating a schema? Is it creating a temporary schema table? Is it doing optimizer stats on that to make the query? What's it doing?
Yes, it's great. This works with JSON files, it works with CSV files, it works with Parquet files, it works with a bunch of other stuff.
It works with this Excel, doesn't it? Can you do it?
Yeah, I think somebody made a plugin. I don't see everything happens in DuckDB anymore, but like... So with the JSON files, what happens is, you say select star from... By the way, select star is optional. You can just say from JSON file in DuckDB now.
Oh, okay.
We have blog posts on friendlier SQL where we innovate the language just to, make people happier. So if you say select star from JSON file, what will happen is that our query analyzer will say, from file name, I would expect a table name there. I do not know such a table. Therefore, I'm going to do what we call a fallback scan, where we look for other things that could potentially be treated as a table. In this case, it finds, it will go through various sort of extensions. It will say, does the file name end in Parquet? No, it ends in JSON. Aha. Let's ask our JSON reader to look if it potentially can read this file. What does the JSON reader do?
Yeah.
It will open the file and see if this file exists. If it exists in the JSON file, it says, I can do this. Then in the binding phase, I mentioned this earlier, is the phase where we collect the types and the data column names and the table names and all set for our query. We will actually run code that will try to create a temporary schema for your JSON file. And so that will there's I think by default it will sample your JSON file and not, because it can be gigantic and you don't want to read the whole thing, blah, blah, blah. Not entirely sure. I didn't write the JSON reader. But it will generate this temporary schema for you. And then basically the names will be, from looking at the file, it will know the names. It will know the types. Okay, this is an int, this is a string, this is a timestamp or whatever JSON has. And then with that information, it can resolve the rest of the query. So if you say select star from JSON file where A is 42, it will say, aha, is A a field in this file? Yes, it is, because it just generated a temporary schema. The binder will be able to use this in resolving the rest of the query. And then during query execution, actually no dedicated importing step happens. What happens is that we do a streaming read on the file directly, and we treat it if it were a table. Like DuckDB has this notion of treating a lot of things like they were tables, like also stemming from, by the way, this whole integration in the same process kind of idea, because we realized that once we're in the same process, we can treat a lot of things that exist in this process like if they were tables. For example, if you're in Python, you can treat like a pandas data frame as if it were a table and just query it directly.
Okay.
So in this case, JSON, it treats as a table. There's code in DuckDB that essentially can read a bunch of bytes from the JSON file, emit the vector chunk, intermediate thing that the rest of the stack can understand, and it all happens sort of dynamically, and that temporary schema only lives as long as the query lives.
Okay. And if it's sampling, then you don't need to read the whole file multiple times before we can start the work.
No, I think you can make it to read the whole file, because sometimes JSON files are very irregular, but very, very often they're also very regular, right? Like, the sadness about JSON files sometimes is that they are indeed exported from relational databases, only to be read back into relational databases. There's only one thing that can go worse there, which is like if somebody does this with XML files, but that's hopefully, you know, I
won't criticize JSON too much, because it's a miracle we managed to mostly agree on a universal file.
I'm not against JSON. I just said, like, JSON is fine. I'm happier with JSON than with XML. Yeah. But this works with lots of file formats. Like, we can do, as I said, Parquet files.
Does it do something similar for the optimization phase? I mean, you've got to gather some. Do you sample some statistics from the top of the file?
No, actually, we can't, because the statistics we have to be exact, or at least out of bounds. So, for example, if we want to do some static proving that a filter can never be true. So, if you say select star from JSON file where a is bigger than 42, our optimizer normally would say, let me look at the min-max statistics. If a is never bigger than 42, I can just remove this filter entirely and return an empty set and be like, done. This is the fastest query ever. I can statically prove there cannot be a result based on the available statistics.
Okay,
we do that. In the JSON case, we don't. We don't have the statistics. The optimizer can work without those statistics. And then it will just have, it won't be able to do these kind of optimizations. If you want these kind of optimizations to be done, you have to copy the JSON file into an internal table, and then it will have all this information.
Okay.
But DuckDB has also really great support for nested types, like, you know, repeating fields, structured fields, these kind of things. So these go natively into columns in our background storage. They're compressed. Like, it works pretty well. There are file formats like Parquet that do have statistics, and if Parquet files have in their metadata things like min-max statistics and a null count and things like that. Right. And we do use those if they're present. So in a Parquet file, if you did this thing where a is bigger than 42, and we can, based on the metadata, derive that there cannot be any value that matches this criterion, we will also just be like, done. Cool. So that depends on the input format. If you can actually write your own plugin.
I was going to ask.
Yeah. So if you have a data like format out there that we don't support yet, DuckDB has this concept of plugins, or we call them extensions, that can provide their own scan functions, we call them. And so those scan functions can be it's just whatever you want them to be. And they have to basically do two things. They have to be able to generate this temporary schema based on some input.
Right.
Like the binding, what I said earlier. And they have to be able to read this thing and produce our intermediates from this input, like our column format or our column chunk format with the 2048 values in it.
So I could create my own plugin that read Apache HTTP log files.
Yes, absolutely. Although our CSV reader would probably be okay at reading those. I think we have the world's most advanced CSV reader. We actually have a PhD in computer science. Does nothing else than work on our on our CSV reader. Again, not because we love CSVs. We actually don't, and he doesn't. He's quite miserable sometimes. But because we realize it's the first thing people do with the data system is they throw a bunch of CSV files at it, right?
Yeah.
So because of that, you need this to be good, and you need it to be fast. I mean, we want it to be fast. We care about this sort of thing.
You've got to meet where they are.
The world runs on a bunch of CSV files. Who am I to? I can whine about this on Twitter, but like, who's helped by that? I can also be like, right, get to work. That's
nice.
Glad to hear it worked for you.
It really is. So thank you very much for taking me through how it works.
Pleasure, Chris.
Oh, cheers. Hannes, I'll see you again.
Thank you.
Thank you, Hannes. And I'd like to dedicate this whole episode to Hannes's dad for selling his son a bricked computer. I'm all for teaching your kids to be independent problem solvers, and I think we've just seen the fruits of doing that. But bricked computer, that is a next level move. Good parenting, Hannes's dad. If you would like some more next level moves and next level ideas of a different kind, have a look in the show notes. You'll find links to all the papers that Hannes mentioned. And if you'd like something a bit more accessible to go and play with, have a look at DuckDB at duckdb.org. They're not sponsoring this, it's just very quickly found a useful place in my toolbox, so thumbs up from me. Go kick the tires on it. Before you go and kick, take a moment to click the like, rate, share buttons. I live for the brain food of these podcasts and the interesting conversations I have, but I also live by a bit of feedback, so if you leave some, thank you very much. And make sure you're subscribed, because we'll be back next week, of course, with another great mind from the software world. I've been your host, Chris Jenkins. This has been Developer Voices with Hannes Mühleisen. Thanks for listening.